Fog and cloud computing. Cloud computing is a service that offers on-demand access to a shared pool of configurable computing resources, often deployed off-premises. These resources can be made available quickly with minimal management effort. Cloud service providers use data centers for their cloud services and cloud-based resources. To ensure availability of data services and resources, providers often maintain space in several remote data centers. Cloud computing supports a variety of data management issues like enable access to organizational data anywhere and at any time, and streamlines the IT operation of an organization by subscribing only to needed services, and eliminates or reduces the need for on-site IT equipment, maintenance, and management, or reduces the cost for equipment, energy, physical plant requirements, and personnel training needs. Also enables rapid responses to increasing data volume requirements. With its pay-as-you-go model, cloud computing allows organizations to treat computing and storage expenses more as a utility rather than infrastructure. In business terms, this means that initial costs are required to set up an IT infrastructure, which are now transformed into operating expenditures. Currently, there are over 3,000 data centers in the world that offer general hosting services to organizations. There are many more data centers that are owned and operated by private industries for their own use. Cloud computing offers services in the following areas. First is the IaaS, Infrastructure as a Service. This includes hardware, including servers and other infrastructure components that are supplied by a provider and adjusted on demand. The provider handles system maintenance, backup, and continuity planning. Next is PaaS, or Platform as a Service. So a provider provides platform, servers, storage, and operating system for users to develop and launch applications. Also, we have mobile PaaS, MPaaS. This provides supply development capabilities for mobile application designers and developers. And we have SaaS, Software as a Service. Software such as messaging, IoT data processing, payroll processing, gaming, and tax preparation is licensed on a subscription basis and hosted on cloud servers. Cloud services are services offered by cloud providers that are hosted off-premise and available on demand. Cloud customers have access to a shared pool of configurable computing resources that can be rapidly provisioned and released with minimal management effort. Because of the high availability and great resource scaling properties of cloud services, these services are a great way to extend the functionality of an IoT system. Data processing and storage can be done in the cloud instead in the IoT devices. Because the services are all hosted in the cloud, data and resources are always available to any device in the system as long as the device has internet connectivity. Cloud service providers are also very serious about security, ensuring customer data is kept safe and secure. An IoT system that requires server communication such as cloud data analysis could benefit greatly from a cloud computing service. The following are examples of cloud services. We have Amazon AWS. These are cloud computing, which is a cloud service. AWS is a cloud service that provides cloud-hosted, on-demand computing as a service. And with cloud computing, a user can deploy and start using computers in a matter of minutes. Because the service is designed to be on demand, users can start with low hardware resource and expand as needed. Amazon provides a great cloud computing service called AWS, or Amazon Web Service. We also have AIFTTT, which stands for if this, then that. It allows for special resource URLs to be created and mapped to specific IFTTT actions. Imagine you want to receive an SMS message on your cell phone every time someone walks in front of your house. You can easily install a motion sensor capable IoT device to track movements, but the exchange between that device and the cellular messaging system will take some work. IFTTT, it masks the complexity by allowing your movement tracking device to send SMS messages by simply accessing a web URL every time the motion sensor detects movements. Many actions are currently supported by IFTTT, making it a useful cloud service for IoT. Then we also have Zapier. This is similar to IFTTT. Zapier also allows for cloud-based automation. And the main difference between two services is that Zapier is more business-driven, supporting more applications and actions. Another important difference is that Zapier is only free if you have up to 5 actions configured. And if more zaps are needed, a paid account must be created. We also have WebEx Teams. These are app-centric cloud-based service that provides a complete collaboration suite for teams to create, meet, message, call, whiteboard, and share regardless of whether they are together or apart in one continuous work stream before, during, and after meetings. This is built to help teams work seamlessly. It is simple, secure, complete, and open, and provides a space for people to work better. A fog computing model identifies a distributed computing infrastructure closer to the network edge. It enables edge devices to run applications locally and make immediate decisions. This reduces the data burden on networks as raw data does not need to be sent over network connections. It enhances resiliency by allowing IoT devices to operate when the internet connection is lost. It also enhances security by keeping sensitive data from being transported beyond the edge where it is needed. Fog computing extends cloud connectivity closer to the edge. It enables end devices such as smart meters, industrial sensors, robotic machines, and others to connect to a local integrated computing, networking, and storage systems. Fog computing includes a combination of hardware and software solutions, and all fog applications monitor or analyze real-time data from network-connected things and then take actions such as locking a door, or changing equipment settings, applying the brakes on a train, or zooming in with a video camera, or opening a valve in response to a pressure reading, creating a bar chart, or sending an alert to a technician to make a preventive repair. The action can involve machine-to-machine communications and machine-to-people interactions. Simply put, data in motion is a term used to refer to the process of extracting value from data while it is being generated. This data may or may not eventually be stored. It is possible to think of data in motion as telling a story as it happens. On the other hand, data at rest is data that has been stored. A variety of industries that rely on extracting value from data before it is stored make use of data in motion. This includes retail, healthcare, manufacturing, energy productions, public sectors, and service provider markets. With the right infrastructure, data in motion becomes faster and cheaper to use than data at rest because data in motion is easier to locate and it does not need to be stored. And the proliferation of devices in the IoT is one of the primary reasons for the exponential growth in data generation. While the number of sensors and other end devices grow exponentially, mobile routers are increasingly used to better manage internet traffic for systems that are literally on the move. Mobile routers are deployed in airplanes, commercial vehicles, and even in personal automobiles. Not only is the IoT growing, but its boundaries are actually moving. Just as the advent of wireless roaming improved internet access, the implementation of mobile networks is changing the psychology and behavior of consumers and businesses by raising the bar for anytime, anywhere, and on-demand access. Data has become more and more important in business and everyday life. This exponential growth of data has created a new area of interest in technology and business, which we call as the big data. In general, big data is data that is so vast and complex that it becomes difficult to store, process, and analyze using traditional data storage and analytics applications. Big data is typically characterized in three dimensions: volume, velocity, and variety. Volume describes the amount of data being transported and stored, and the current challenge is to discover ways to most efficiently process the increasing amounts of data, which is predicted to grow 50 times by 2020 to 35 zettabytes. Velocity describes the rate at which this data is generated. For example, the data generated by a billion shares sold on the New York Stock Exchange cannot be just stored for later analysis. The network infrastructure must be able to immediately respond to the demands of applications accessing and streaming the data. The characteristics of big data require drastic changes in the way it is supported. The computing platform must be able to process it, and the network must be able to transport it. The storage system must be able to store and retrieve it, and the security measures must be taken to protect it. Data is very valuable. Consequently, it is the main driver behind advancements in technology. Big data has driven the creation of many new approaches to storage and computing. So examples of open source projects that deal with various aspects of storing or computing and transmitting big data sets are Apache Hadoop or WebEx Teams, Cassandra, and Kafka. Depending on the IoT applications, IoT devices may be required to store data for a period of time before sending it out for processing. This scenario is common with devices that do not maintain constant connections to their gateways or controllers. A good example of this situation is vehicle trackers installed in transport trucks. The system may be built to tolerate periods when the trackers are out of range and cannot communicate to transmit the location of the truck. If this happens, the trackers will store the data in the device itself. As another example, consider a connected car. If damaged beyond repair, the insurance company may choose to auction it, along with the owner's data still stored in the car storage devices. In both examples, the data should be kept encrypted to avoid tampering or data theft, and data and laptop storage devices have included support for built-in encryption for a while now. Known as self-encrypting drives, these storage devices stand out because the encryption capability is built into the drive controller, allowing encryption and decryption to be done by the drive itself, independent of the operating system. Cloud services often rely on servers to provide service, and data stored in these servers must also be encrypted to avoid data tampering or theft. And regular backups are also mandatory to minimize losses in case of a disaster. IoT are often small, inexpensive devices with little to no security. Although such devices are computers, they rely on constrained memory and computing resources and may not support complex and evolving security algorithms. Modern encryption algorithms may require more processing power than what is available in the IoT device. In addition to physical security, the IoT device must be able to protect its own firmware and the data it transmits. If data is not properly secured through encryption, it can be intercepted, captured, or manipulated while in transit. Any of these actions may compromise the confidence of the system and makes the data unreliable. To make this problem or to mitigate this problem, ensure that IoT devices are running the latest version of their firmware and protocols. Also ensure that any communication is done using protocols that provide secure encryption by default, and the encryption algorithm must be strong, with other algorithms tending to present exploitable weaknesses. Servers and cloud endpoints should also be secured and use strong encryption algorithms before communicating with IoT devices. If the IoT device relies on an intermediary device such as a gateway or controller, this intermediary device must also use strong encryption. Naturally, intermediary devices should also be kept up to date with the latest software to keep the device from becoming the weak link that breaks the chain. Chapter summary. So for this chapter, personal information related to health, location, wealth, personal reference, and behavior is passing through the IoT devices in increasing volumes, and this increase in volume elevates the relevance of increasing the attention on data privacy and data protection. And new wireless technologies and protocols such as Zigbee, Bluetooth, 4G, and LoRaWAN have been developed to accommodate the diversity of IoT devices. Wireless technology is selected based on the range of coverage, bandwidth requirements, power consumption, and deployment location. Wireless security considerations include selecting a secure protocol, protection for management frames, identification of frequency jamming, or detecting rogue access points, and using security at the application layer. Cloud computing is a service that offers off-premise, on-demand access to a shared pool of configurable computing resources. Cloud computing offers services such as IaaS, PaaS, MPaaS, and SaaS. A fog computing model identifies a distributed computing infrastructure closer to the network edge. It enables edge devices to run applications locally and make immediate decisions. The proliferation of devices in the IoT is one of the primary reasons for the exponential growth in the data generation, and data can be deemed at rest or in motion. Big data is typically characterized in three dimensions: volume, velocity, and variety. Data stored in servers must be encrypted to avoid data tampering or theft, and regular backups are mandatory to minimize losses in case of a disaster. And last is IoT devices should run the latest version of firmware and protocols, and any communication between devices, it should be done using protocols that provide secure encryption by default. And this ends this chapter, chapter 4. I'd like to thank you for listening. Keep safe, and together we learn as one.